Hello everybody, welcome back to another Civi quiz tutorial. In this tutorial we're going to be covering quiz number 22, which first introduces the elasticity tensor. Now, as you guys may remember from the past weeks, our first big topic after the midterm was strains. We figured out the small strain matrix, the green strain matrix. Then after that we kind of changed directions and we started talking about stresses, and we figured out the Cauchy stress matrices. So by the end of these two topics, we know a lot about strains and we know a lot about stresses and we know a lot about their tensors and their tensor properties. So now we're going to do kind of the unthinkable and try and say, okay, well, if I have a strain tensor, can I find a stress tensor or vice versa? Because this is how we do analysis, as you guys will see at the later stages of this course. Now, before we begin, I just want to make a quick note. I'm changing the video format a little bit. I want to try and improve the quality, make these videos a lot nicer for you guys. So if you guys like the new format, please let me know. Please give me any suggestions, of course, if you guys have any things that you guys feel I can do better. These videos are for you guys. I want to help you guys learn to the best of my abilities, and if there's something obvious that I'm obviously overlooking, please let me know so I can try and include it in future videos to make all you guys happy, because at the end of the day, that's what this is about. These videos are for you guys. Alrighty, with that being said, let's jump into the theory of the elasticity tensor. Alright, so let's take a step back and try and look at 398 as a whole. What have we covered since the first day you guys, I was going to say came to class, but basically turned on Zoom and looked into the class? So the first thing that we really talked about was linear algebra. And we figured out, well, linear algebra, it's pretty useless in a physical sense, in a meaningful sense. We were just learning about matrices and how to find their properties, such as eigenvectors, eigenvalues, norms, etc. But then we started applying that to the real world in the form of strain tensors. So a tensor is just a matrix, and we started talking about the stress matrix or the stress tensor. And from there, we said, okay, well, now that we're experts in strain, let's start looking at stresses. So then we looked at the Cauchy stress matrix, and we figured out a lot of the properties of the stress tensor. So at this point in time, we know two major things. The first one is the strain tensor, or the small strain tensor. Of course, we know that there's a green strain tensor, but for the majority of problems in this class, we're going to be talking to or referring to the small strain tensor. So here it is. One nice property of it, of course, is it's nice and symmetric, and that makes our lives easier because we only need 6 components to find the whole small strain tensor. And of course, this comes from the displacement gradient, which you guys know all about right now. Now, after we were done talking about strain, we moved on and said, okay, well, what about stress? Because every time you hear stress, you hear strain or vice versa. And we said, well, there's a nice stress tensor called the Cauchy stress tensor. And much like the strain tensor, it was nice and symmetric. So if we had the 6 components, we can easily figure out the Cauchy stress tensor as a whole. Now, what we're going to do moving forward is saying, okay, well, I know a lot about the stress and I know a lot about the strain. Well, there must be a relationship between them. Let's say I run an analysis and I put a load on a building. If I know the load, I know the stresses, but I don't know the strains. So the question is, well, if I know the stresses, how can I find the strains? And the opposite can be said. Let's say I'm simulating a building, but instead of applying a load, I apply an earthquake. And an earthquake's a displacement. I'm moving the bottom of the structure. If I know the displacements, I know the strains. Well, how do I find the stresses if I know the strains? So that's kind of the last major goal we're going to try and cover, is how can we convert from strain to stress or from stress to strain? Well, there is a very nice relationship, and I use the term very nice really loosely because it either be quite nice or it can be straight up hell. As we're going to see, we're going to mostly deal with the nice case, so for you guys, it'll be very nice. So we can define the stress and strain as vectors, and we can create a map between them. So here's the key. We're going to define the stress and the strain as vectors, and then if we have two vectors, well, then we know we use a matrix or a tensor to switch between them. So here's the two vectors that I'm going to represent. On the left-hand side, I have what I call the strain vector. So it's epsilon 1, 1, epsilon 2, 2, epsilon 3, 3. Now here's kind of the one trick that'll get you guys, and you guys will see this in question 5. For the shear strains, so epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3, we have a 2 included. And that 2 just comes from the derivation. It makes things a whole lot nicer. It's kind of like the green strain tensor where we have the 1/2 out in front, stuff like that. So that's there, but we have to be mindful of this too. If we look at the right-hand side, we have a stress vector. So I got sigma 1, 1, sigma 2, 2, sigma 3, 3, and then I got my shear stress is sigma 1, 2, sigma 1, 3, and sigma 2, 3. And notice that there isn't a 2 in front of those shear stresses. It only applies to the shear strains. So how do we find this C? Well, Dr. Sammer, of course, made a nice video explaining where C comes from. So what you guys need to know is that C is a 6x6 symmetric tensor consisting of 21 coefficients. So before we discuss the 21 coefficients, let's kind of take a step back. What C actually is an 81 coefficient tensor. However, it simplifies down to 21 coefficients due to the symmetry of the stress and the strain matrix. Now, it simplifies down. C is not symmetric because of the symmetry of the stress and the strain matrix. It simplifies down because of the symmetry of the stress and the strain matrix. We'll discuss why C is symmetric in one of the example problems. But I know what you guys are thinking. Clayton, you said this was going to be easy, but there's 21 coefficients here. How the hell is that easy? 21 coefficients? I'm not going to be able to remember any of those. Well, we can see that these 21 coefficients can be nicely simplified depending on the material behavior. So two major ones that we're going to cover in this class is isotropic material behavior and orthotropic material behavior, where the isotropic one is the very nice one, and luckily for you guys, that's the majority of our problems. So let's jump into it. So a linear elastic isotropic material. I know it's quite a mouthful to say, and of course not in a good way. So linear elastic, well, that has to do with the loading, how it handles, but isotropic, that's the key here, and that's why I have it in bold. Because the response of an isotropic material is independent of the coordinate system. And why is that really nice for us? Well, that matrix C that we have can be simplified into the following 6x6 tensor. And if we look at it, we see that we have three variables. We have a V, which is the Poisson's ratio. We have an E, which is the Young's modulus. And you guys are saying, oh, I already know those from 270. This is a piece of cake. And then we have G. And then you guys are saying, oh, hold up, Clayton. I don't remember G. Or maybe you guys do. I don't really remember 270, but G is what we call the shear modulus. But luckily for us, G actually simplifies into E divided by 2 times 1 plus V. So in essence here, we only have two parameters. We have the Young's modulus and the Poisson's ratio. And if we know those two, then I have the relationship between stress and strain, which is great because it's easy to solve for in a computer analysis. So now let's talk about the second type I discussed with you guys, and that is a linear elastic orthotropic material. So linear elastic stays the same, and that is something that will always stay the same in this class. If Dr. Sammer decides to give you a plastic material, well, all I can say is good luck. And the same if it's nonlinear. Those are kind of more advanced problems, even problems that graduate students have a lot of trouble dealing with, because there's a lot of factors you need to consider. So we're going to keep it linear elastic, but now we're saying it's an orthotropic material. And what does that mean? Well, the response of an orthotropic material is dependent on the coordinate system. So, as we can see from the matrix, it holds a very similar format to an isotropic material, but instead of just having one general Poisson's ratio, one general Young's modulus, and one general shear modulus, we can see that they're distinct depending on the direction. For example, if I'm looking at the Young's modulus E, it's not just E anymore. It's E11, E22, and E33. And you're saying, well, Clayton, surely we're not going to have to deal with this. There must be some sort of nice similarity that we can take advantage of. And the answer is yes and no. So orthotropic materials, they're gross. No matter what you try and do, they're always going to be a little bit gross, as you guys will see in question number 5. However, there is one nice feature we can take advantage of, and that's remembering that that C tensor, the relationship tensor, it is symmetric. So if I look at, let's say, the shear in positions 1, 2, in the tensor, I have negative V21 over E22. Well, that has to be symmetric. So therefore, that's equal to V12 divided by E11. So we're going to use this symmetry, as you guys will see in question 5. The symmetry makes it a little bit easier, but in the end, it's still pretty gross. So don't get too reliant on the symmetry. Things are still not going to be too nice. However, a little tip between us, orthotropic materials, because they're so complex, chances are you won't see too much of them on the midterm. And if you guys do, it'll be in a very limited scope. So don't be too worried too much. However, if you guys go to grad school and take Dr. Sammer's 664 solid mechanics class, get ready for orthotropic materials because he hammers you with them. So on one concluding note, if we want to define an orthotropic material, we need 9 parameters. As you guys will see in question number 5 in the quiz, they give us 9 parameters and we're going to have to go through them all. So that concludes the theory. Hope this kind of clarified some things for you guys. Again, in my opinion, and this is my opinion, so please don't take this, take it with a grain of salt. Let's put it like that. This is the last real complex subject of 398. After this, I find it smooth sailing from here. So once you guys understand this, you guys are good to go. All right, guys, let's jump into the quiz. Alrighty, guys, welcome to the quiz. As you guys will see, this quiz is 5 questions, and they're not too bad with the exception of question number 5. It's a little bit of work, but in the end, you guys will be able to understand it just perfectly. You guys are really smart. So, question number 1 says, in a linear elastic structure, the matrix of coefficients relating the stresses and the strains is symmetric as a result of, and it gives us 4 different options. So, the first option is the strain tensor being symmetric. The second option, the stress tensor being symmetric. C, both the strain and the stress tensors being symmetric. Or D, the strain energy inside the body is independent of the path of deformation. Now, if I was looking at this on a multiple choice and I didn't really know the answer, of course I'm going with one of A, B, or C. They're all kind of related, and part D looks like it's in a whole different ballgame. So I assume that it'd be part A, B, or D, or choices A, B, or C, sorry. But however, the answer to this question is actually D right here. So the answer to the question is the strain energy inside the body is independent of the path of deformation. So we're going to discuss a little bit of why. So in its primal form, in its most generic form, this C matrix, so as you guys remember, it's a C matrix, it has 81 coefficients. And this is in its most general form without any simplification whatsoever. Now, the symmetry of the stress and the strain matrix, and I would like a kind of a nicer line here, this does help. However, it doesn't help in the way that most people think. Now, because they're symmetric, there is simplifications that can be made. And what happens is the properties of the stress and the strain matrix being symmetric, well, it takes that 81 coefficients and it simplifies it down into 36. And this results in that nice 6x6 matrix we know C to be. However, this does not prove any sort of symmetry. Where the symmetry comes from is actually the effects of energy preservation. And because of those effects of energy preservation, this 36, well, that comes down to 21. And the reason for this is because of energy conservation. What this actually means is that this is a symmetric matrix. So the symmetry of the C matrix, it comes from energy preservation. It doesn't come from the strain tensor or stress tensor being symmetric. However, it always should be noted that, of course, the symmetry of the stress and the strain tensor, it does help because it brings those 81 coefficients down to 36. And then from there, we can apply energy preservation to go from 36 down to 21. All right, so that's it for question number 1. Let's jump to question number 2. All right, so question 2 is going to be the question that I know a lot of you guys will have questions about because that has to do with energy. And up until this point, we haven't really discussed energy. So of course, it's going to be foreign and raise a lot of concerns. However, don't worry about it. The concept of energy isn't too bad. You guys will become very familiar with it in the coming weeks as it is one of the topics moving forward. So let's jump into the question and see what exactly it has to say. So question number 2 says a linear elastic material has a Young's modulus of 1000 MPa and a Poisson's ratio of 0.2. If the stress is changed from sigma 1 to sigma 2, and I drew sigma 1 and sigma 2 down there, it says, what is the total change in strain energy stored in the material due to the deformation associated with the change in stress? So if we look closely at sigma 1 and sigma 2, they are the exact same. However, the 10 MPa for sigma 1,1 changes to 20 MPa for sigma 2,2. As we can see, sigma 2,2 remains at 10 in both states. So the only change is there's an increase of 10 MPa for sigma 2. Now, we got to figure out, okay, well, what exactly is this strain energy? So let's come down here and let's draw a nice little plot, because once you guys understand the plot, you guys will say, oh, okay, this question isn't too bad at all. So what I'm going to do is I'm going to draw a stress strain curve. And I don't know why I drew 3 right here. Strain's the other way. I must be thinking backwards today. So of course, it's nice and linear elastic, so it's going to have this kind of behavior, nice and linear and nice and elastic. So we're going to consider 2 points. The first point is at 10 MPa for sigma 1, and the second one is at 20 MPa. So what happens is this is going to be our stress number 1, and this is going to be our stress number 2. And what happens is the strain energy is actually the area under this curve. So if I were to draw a little dot here, this is going to be the strain energy of sigma 1. And then if I were to draw a dotted line here, well, all the way to 0, this is going to be the strain energy of number 2. So all we're really doing is taking the area under these curves. And if we know, well, okay, this is a nice triangle. So of course the strain energy is going to be the area. Well, it's a triangle, so it's going to be 1/2 of the stress times the strain, which is epsilon. So if I know the stress and the strain, well, then I can easily figure out what the energy is. Now, if I look up above, I look and I say, okay, well, I got sigma 1, or I guess I got sigma 1 and I have sigma 2. So in both cases, I do know the stress. However, I have no idea what this strain is over here. So that's going to be the goal is we know the stress, we're going to need to find the strain. And once we find the strain, well, then we substitute everything into this nice formula and figure everything out. So we come down here and say, okay, what exactly do we know? Well, we know that this, and I'm going to switch colors here because I find that pink shows a little bit brighter. We know that we have a linear elastic, so I'm going to put linear elastic. So this is nice. This describes the behavior above. And then we know it's going to be an isotropic behavior because we don't mention orthotropic at all. And we're just given one Poisson's ratio and one Young's modulus. So of course it's going to be isotropic. And of course we're dealing with material. So I'm just going to put material here just to kind of complete the sentence. Now, because it's a linear elastic isotropic material, we know that there's a nice C matrix that describes the relationship between the stresses and the strain. What exactly do I mean by that? Well, it means that if I have the strain as a vector, this is going to be equal to some strain or relationship matrix C multiplied by the stress tensor. And this is exactly what we want, because if we remember what we have the stresses. The stresses aren't a problem. And if we have C, because it's a linear elastic isotropic material, well, then I can solve for the strains. And once I solve for the strains, well, then I can solve for the energy. So I'm going to do a quick cut here and expand out this formula to show you guys exactly what this formula means. All right, so I just finished writing out the nice long stress tensor that describes the relationship between the stresses and the strains. So a couple of things I want to highlight before we get into it a little bit more. Remember that when we're talking about the strain vector, all of the shear strains have that 2 in front of them. If you guys forget this 2, especially in question number 5, you guys are going to get the wrong answer. So there's kind of the first thing that we're going to want to keep in mind. Now, let's actually look at that relationship tensor C and try and figure out what exactly it means. Well, if we look inside, it's not too bad. There are a lot of zeros, and I mean a lot of zeros, so that's great. And if we look at the amount of variables, there's 3. There's E, which is the Young's modulus, and you're saying, all right, well, we were already told that's 1,000, so that's good to go. There's V, well, again, that's the Poisson's ratio, and we were told that was 0.2, so that's not bad at all. And finally, there's G. Well, we weren't told what G is, but if we look down below, there's a nice formula for G. And all we need to do to solve for G is have E and have the Poisson's ratio V. And we have both of those, so technically we already know G as well. Now, what we do is we multiply this this relationship tensor C by the stress vector. So if we look at my stress vector, I simplified it a little bit, and I said, okay, well, in both of those stress states, there isn't a sigma 3,3, there's no sigma 1,2, no sigma 1,3, or no sigma 2,3. All we have in that stress tensor is sigma 1,1 and sigma 2,2. So what I did is I put the rest to 0, and I have my stress vector now in terms of sigma 1,1 and sigma 2,2. And what I'm going to do is I'm going to solve for the strains in terms of sigma 1,1 and in terms of sigma 2,2. So in the end, I'll have a nice equation, and then I can start playing around with it. If you guys want, though, however, of course, you guys can sub in sigma 1,1 is equal to 10, sigma 2,2 is equal to 10, and start finding the actual values of strains. However, since I have to do it in 2 cases, I'd rather just find one nice equation, and then I can apply it to both fairly simply, as you guys will see. However, again, there's many ways to do this. You guys can pick whatever way feels the best for you. So I'm just going to come down a little bit. I'm going to say, okay, well, if I'm looking at this strain vector, I have everything on the right-hand side. So what I'm going to do is just simply go in Mathematica and throw everything on that right-hand side in. And what do I get? Well, I get this right here. So if I look at my strain vector now, as I can see that I'm going to have non-zero components for all of the normal strains. So I see that epsilon 1, 1, epsilon 2, 2, and epsilon 3, 3 all have some sort of components. Meanwhile, all my shear strains, epsilon 1, 2, epsilon 1, 3, and epsilon 2, 3 are all equal to 0. Now, you guys are maybe saying, Clayton, why did you do all the matrix math? These equations are given to us by Dr. Sammer very conveniently in his textbook. So if I want to convert to stress or strain, he gives us nice equations. You guys can use them, sure. I just want to show you guys where exactly everything comes from, and that is from this right here. It comes from that matrix C and multiplying the stress and the strain, stuff like that. So now that I know the now that I know the strains in terms of the stresses, I can start figuring out what the energy is. So what I'm going to do is I'm going to come up to the top here, and I'm going to remember my nice energy formula right here, where my energy is equal to 1/2. And again, that's because we're taking the area under the curve, and it's a nice linear curve. So you basically have a triangle multiplied by the stresses multiplied by the strains. So I'm going to come down here. I'm going to say, okay, well, U, which is my energy, is going to be equal to 1/2 the stresses times the strains, and say, okay, well, that's not bad. All I'm going to have to do is go 1/2. And then what I'm going to do is I'm going to go through and I'm going to multiply all the stresses by the strains. So I'm going to scroll up to the very top here and say, well, my first stress that I always have is sigma 1, 1. Both in sigma 1 and sigma 2, those two different tensors, I see that both of them have non-zero components of sigma 1, 1. So I'm going to come down here. And again, right now, I'm trying to keep it as general as possible. I'm going to put sigma 1, 1. So that's my stress. And I'm going to have to multiply this by its corresponding strain. Well, of course, if I'm dealing with sigma 1, 1, then we're going to be talking about epsilon 1, 1, which is that first component right here. So right here, I have 1 divided by the Young's modulus, and then multiplied by sigma 1, 1 minus Poisson's ratio sigma 2, 2. And that's it for sigma 1, 1. Again, I just took the stress and I multiply it by its corresponding strain. Now I'm not finished yet because there's other non-zero stress components. So I'm going to go plus. I'm going to look up at the top and say, okay, in this case, I have a non-zero component for sigma 2, 2. So what I'm going to have to do is I'm going to have to bring down sigma 2, 2 and say, okay, in this case, I have a sigma 2, 2. Well, what is the corresponding strain with sigma 2, 2? Well, that is this one right here. And I say, okay, well, it's very similar to before where I have 1 divided by the Young's modulus, but in this time it's a little bit reversed where I have sigma 2, 2 minus Poisson's ratio sigma 1, 1. Now, if I wanted to, I can include the terms for sigma 3, 3, but it would just be 0 times something. And I see that the rest of the components are indeed zeros. So I can conclude that my strain energy is actually equal to this formula right here. However, this formula looks a little gross. So what we're going to do is we're going to come down here now that we don't really need to see the matrices. And we're going to say, okay, well, so upon some simplification, I can say that my strain energy U is equal to 1 divided by 2 times the Young's modulus multiplied by sigma 1, 1 squared plus sigma 2, 2 squared minus minus sigma 1, 1 times sigma 2, 2 times the Poisson's ratio V. So now I have a nice equation that finds my strain energy depending on whatever stress matrix I want to throw in there. So for example, if I say, okay, well, I'm looking at the first one. So sigma 1, well, I can say the strain energy 1, this is going to be equal to 1 over 2 times the Young's modulus. Well, we're given the Young's modulus is simply 1,000, so I'm just going to put 1,000 in. Nice and easy. And I'm going to multiply it by all the components. So the first one is sigma 1, 1 squared. I can just scroll up to the top real quick. Well, sigma 1, 1, that is simply just going to be 10. So I'm going to come down here and say, okay, well, the first one is going to be 10 squared. I could say, all right, well, we're going to add that to sigma 2, 2. Well, sigma 2, 2, that was also 10. So it's going to be 10 squared. And then minus, we have sigma 1, 1, which is 10. Sigma 2, 2, which is also 10. And then the Poisson's ratio, which we were given as 0.2. So I put all this in brackets. what happens is you guys get a very small answer. Now, when I usually get answers like this, I think something's wrong. But when we're dealing with the strain energy, the answer will be small. In this case, I get 0.08. So there's my answer for the first one. Not too bad at all. I can say, all right, well, now I got U1. What about the strain energy 2? So I'm going to go do the exact same procedure. I know that the first part is 1 divided by 2e. Well, it's the same in both cases, so I'm going to have 1 divided by 2 times 1,000. So I'm going to put this in. I'm going to go look at the components. So if I look up at sigma 2, I see that the first component is 20. The second component is 10. So I'm going to come down here and say, all right, I'm going to have 20 squared plus 10 squared minus 20 multiplied by 10. And then, of course, we multiply by the Poisson's ratio to end it off, which is simply 0.2. Now, when I do this, again, I get a very small answer, so don't be scared when you guys get small answers. This one is 0.21. And now that I know both U1 and U2, and the question's asking for the difference between them, I can simply say that my change in U will be equal to U2 subtracted from U1, which is going to be equal to 0.21 minus 0.08. And if I do that, well, it's pretty simple math. I get that delta U is equal to 0.13. So I'll just write it kind of down here a little bit bigger so everyone can kind of see what my answer is. My delta U is equal to 0.13. And that's how you guys do a question like this. Again, it looks pretty complicated, but the main thing to realize is that energy is just the area under the stress-strain curve. And we're going to talk about that a little bit more moving forward, because when we load something and then unload it, as you guys will see, since it follows the same path, there technically is no energy under the curve. But again, that's something that we'll see a little bit later, so don't worry about it too much for right now. Right now, let's worry about question 3, which we're going to start right now. All right, so moving on to question number 3. Nice, short, little, easy question. I know you guys love those nice, short, easy questions, and so do I. It makes my life a lot easier. So let's jump into it. It says, consider an orthotropic material whose axis of orthotropy are aligned with the coordinate system. Then the Poisson's ratio V31 is defined as, and it gives us 4 different options. Now these options can be basically split into 2 decisions we have to make. The first decision is it going to be the negative ratio of epsilon 11 divided by epsilon 33, or the negative ratio of epsilon 33 divided by epsilon 11. And then the second thing is the material being stretched along direction 3, or is the material being stretched along direction number 1? So the key to this is understanding what the 2 numbers mean. So let's look right here. So we got V31. The first one, which is the 3 in this case, this is the axial direction. So this is going to be very important because we can already answer the second question that I asked at the beginning. But before that, let's talk about the second one. The second number here, which is the second number, which is the 1 in this case. I'm getting confused. The second, which is the 1 stuff. I'm sure you guys are getting just as confused as I am. But the second number in the subscript, which is a 1 in this case, this is the transverse direction. So transverse direction. So right from here, we can figure out the second question I asked, which direction is the material being stretched? Well, the 3 is the axial direction, so we know it's actually going to be stretched along direction 3. So we know it's either going to be A or B in this case. Now, the second part is that the negative ratio of epsilon 11 divided by epsilon 33, or epsilon 33 divided by epsilon 11. And there's not really a way to explain this besides just looking at the definition. If you guys look at the definition, it's the ratio of transverse to axial. So in this case, it's actually going to be the transverse subscript in front. And what do I mean by that? I mean it's going to be answer A right here, because that transverse, which is in this case 1, 1, that goes out in front. So we have epsilon 1, 1, which is the transverse. divided by epsilon 33, which is the axial. So one of those questions that, again, not too hard, very easy to forget, but it's very good to know for the midterm. So that concludes question number 3. Nice little simple question. Let's go on to something a little bit more complex in question number 4. All right, so question number 4, again, it's a nice simple question. It doesn't look simple, but trust me, it's nice and simple. And as you guys will see, it's going to be a piece of cake. So expect something like this on your midterm. Very standard midterm type question when we're talking about the elasticity tensor. So again, remember this, very common midterm question. And the question says, the figure represents a specimen under a confined compression test. And what does that mean? It means that I'm crushing something, but at the same time, I'm preventing it from expanding laterally at the same time. So if we look at the figure, we can see all the arrows are pointed inwards towards the cylinder. And it says the vertical stress is negative P, where P is a positive real number, while the confining pressure is equal to negative 3P. If E is the Young's modulus and V is the Poisson's ratio of the specimen, then what is the volumetric strain? So the first thing that we have to try and figure out is, well, what exactly is the volumetric strain? Because again, we haven't talked about strain in a little while. I know you guys probably forgot. So the volumetric strain, which I just say as epsilon V, is simply just going to be epsilon 1,1 plus epsilon 2,2 plus epsilon 3,3. And this is kind of a measure of how the volume is changing. Now, if I look at this and say, okay, well, all this question wants is the volumetric strain, piece of cake. All I need to do is find epsilon 1,1, epsilon 2,2, and epsilon 3,3 until I realize I'm not given epsilon 1,1 or any of those. Instead, I'm given the stresses, which are all in terms of P. So if I come down here, I can say, okay, well, I actually know my Cauchy stress matrix. So I'm going to come down here. I'm going to say, okay, well, if I look at this cylinder, there's going to be no shear. So it's just going to be diagonal components. So we're just going to have to go through and fill out the sigma 1,1, sigma 2,2, and sigma 3,3. So I'm going to switch colors real quick. So let's go to red and let's define our actual basis. So this right here, this is typically in the cylinder test as E2. We have E1, which comes out this way like this. So this is going to be E1. And then E3 is the one that kind of comes out like this. So it's good to remember this reference because if not, you're going to start mixing up everything. But in the case of this volumetric strain, it's not going to matter too much. So if we do this as a kind of our guide, we can say that, all right, well, in E1 direction, we're going to have negative 3P, negative 3P. In the E2 direction, that's the direction we're compressing the cylinder, we're going to have negative P. And then finally, in the E3 direction, well, that's the same as the E1, where we're going to have negative 3P. And what's nice about these tests, there's no shear, so everything else is simply just going to be 0. So I'm just going to fill in the zeros here. I'll close up the matrices, make it as pretty as I can. One of the things about these new videos is I'm not trying to have the grid lines. So if this looks very not very nice looking, I apologize for that. Hopefully my writing will get better over time. So now as we come to the question, well, all we need to solve this question are the strains, but all we have are the stresses. Luckily for us, we know that there is a very nice relationship where the strain vector can be found using that elasticity tensor C multiplied by our stress tensor sigma. So I'm just going to take a moment here to redraw that from the previous question so you guys can see exactly what I'm talking about. And that is this right here. So as we can see, we have a nice long strain vector. We have a big giant elasticity tensor C in the middle, and of course we have our stress vector over on the right hand side. Now the nice thing about the stress vector is we actually know the components sigma 1,1, sigma 2,2, etc. because we actually have, and I'll kind of make a little note of it over here, we have our Cauchy stress matrix. So what we can do is we can take these values from the Cauchy stress matrix and we can substitute them in as our stress vector. So what I'm going to do is I'm going to erase these because we don't need them as arbitrary parameters because we already know what they're going to be. So the first one, sigma 1,1, well, we know that that is negative 3 times P. Sigma 2,2, that's simply just negative P. And sigma 3,3, that is negative 3 times P. And then, of course, we have no shears, so the rest are just going to be 0. So now all we have to do to find these strains is just solve for the matrix. It's not that bad. Because again, my biggest recommendation to you guys, and this will save you all the time in the world, define this in Mathematica, save that file, and then you guys can always copy and paste this matrix over and over again, so you guys always don't have to try and retype it, or even worse, do it by hand. So we're going to come down here and we're going to say, okay, well, after we do this, what I find is that these are my strains. So just like before, we can see that we have no shear strains, which is great because then we don't have to worry about that trick with the 2 out in front of the strain. And we can see that our only non-zero components is simply E11, E22, and E33. So what I can do is I can come down here and I'll try and keep this into the page as much as possible. And we remember that our volumetric strain, which is what we're trying to solve for in this question, is simply just E11 plus E22 plus E33. Or I should say epsilon. I'm sorry if you guys are getting confused with the E's and the epsilon, stuff like that. So what happens is all of them have 1 over E out in front. So I'm just going to keep this 1 over E in the front and just kind of leave it alone. And I'm going to go through. So epsilon 1, 1, well, that's 1 over E. I've already included that. But then it's negative 3P plus 4PV. Confusing me, where'd you get it? Well, epsilon 1, 1, that's just going to be the first component right here. So what I can do is I already have the 1 over E. I can go negative 3P plus 4 times P times epsilon rho. Perfect. So then I can say, all right, well, now that I got epsilon 1, 1, how about epsilon 2, 2? Well, we know that epsilon 2, 2 is going to be this component right here. Again, I already have the 1 over E out in front, so I just have to include the stuff inside the bracket, which is negative P plus 6 times PV. All right, perfect. Move on to the last one, epsilon 3, 3, 1 over E, and then multiplied by negative 3P plus 4PV. So I'm just going to include this, which is negative 3P plus 4PV, and that's it. So all I'm going to have to do is say, all right, well, this looks like a pile of shit. Let's try and simplify it a little bit at least. And what I get is, just right from the beginning, all the terms have a P, so I'm going to take the P out. Again, it's divided by E, and then I get negative 7 plus 14 times V. Well, I say, all right, well, this still looks a little bit ugly. Let's try and simplify it a little bit more, or in the case, let's try and simplify it in the multiple choice answer that you guys are given. Well, if I move that 7 out inside, I get 7P divided by E, and then I have negative 1. Well, I prefer a negative on the other side to make it look a little bit more clean. So what I'm going to do is I'm going to take the 7 out of the 14. That leaves me with 2V. And then, of course, we have that negative 1 right there. And this is our final answer. So as you guys can see, this question's not too bad at all. The hardest part is just using this matrix C to try and get your values of strains. However, again, please just throw it in Mathematica because then you guys can use it whenever you want. When I was solving this question, I took my midterm code from the solid mechanics course and just copied over the matrix C. It was nice and easy. So that concludes question number 4. And up until this point, as you guys see, the quiz is not too bad. However, with question number 5, this is where things get a little bit spicy. So let's start question number 5. All right, guys, let's begin question number 5. So might as well get a little comfy. This question's pretty long. Grab your popcorn, grab your snacks, grab a nice drink, get comfy, because here we go. All right. Question number 5 says the table lists an orthotropic, and that's how you know that you're screwed right away, anytime you see the word orthotropic. So the table lists the orthotropic elastic material properties of a wood specimen. And that's how you also know that you're screwed. Wood's never fun to deal with, so whenever you see the word wood, just be scared. And it says, as obtained from experimental data with reference in the table. I know you guys probably don't really care about the reference, but of course it's good to cite your sources. So it says variables L, R, and T represent the longitudinal, radial, and tangential directions respectively, which correspond to the natural directions of the wood specimen as shown in the figure. The second figure shows the specimen orientated such that the horizontal directions E1 and the vertical direction E2 form a 45-degree angle with the longitudinal and radial directions. In a coordinate system where B is equal to E1, E2, and E3, the specimen is pulled with a stress sigma 1 equal to 100 MPa. So that's kind of a nice thing where we're only given one stress. It could have been a lot worse. It said, what are the corresponding strain components in the coordinate system B? So there's something that we're going to definitely have to realize and keep note of, is it wants it in the coordinate system B, that original coordinate system. So here's our table. It's kind of small to see, but of course you guys have a big picture if you guys want to. And I don't know if I can highlight this actually. Let's see. Oh, maybe not. All right, but you guys can see where the values are, so I'm not going to go too deep into it. And here's kind of the problem that we face. And what makes this problem really, really tricky. When we look at what we're given all the properties in that longitudinal, radial, and transverse direction. However, the loading does not exactly occur in that direction. Loading occurs in the E1, E2, and E3 direction. So we come down here and say, okay, well, here's our specimen right here. We're pulling in that E1 direction, but of course, our properties are in another basis. So as you guys can imagine, the first thing that we're going to have to do is change our stress into the respective bases of the material properties. So what I'm going to do is I'm just going to scroll down a little bit. I'm going to say, all right, well, of course, in our original basis set, which is B, we can figure out what our stress tensor is. So I'm just going to try and make this as nice as possible. So sigma, of course, it's uniaxial tension, so we only have sigma 1, which we know is 100, and the rest of the components are going to be 0. And this example might get a little bit messy because it is quite a long one. So please excuse my writing, as I know that it is not the nicest when the questions get long. So right here we have our sigma, but again, this is in the basis set B. So what I'm going to do is I'm going to put this as in B is equal to E1, E2, and E3. So the first thing that we're going to have to realize is, well, material, if the basis set of our loading does not match the basis set of our properties, well, it's completely useless. So what we're going to have to do is we're going to have to change this basis into EL, ER, and ET. And if we look at this and say, all right, Clayton, well, how exactly do we do that? Well, we look at the figure here. All we need to do to change from E1, E2, and E3 over to EL, ER, and ET is we're just rotating the basis. So we remember that, okay, well, I can find sigma prime as simply as Q times sigma times Q transpose. And this right here, this will be in the basis set B prime, which is equal to, and instead of E1, E2, and E3, this will be, and I'm going to look, so E1 is going to go to EL, so this will be EL. E2, which is over here, is going to swing over to ER, so this will be ER. And then, of course, out of the page will be E3, which is the same as ET. So this is the first step, is taking our stress and converting it into the coordinate system of the material properties. So if we look at this formula here, well, we know sigma, the only thing that we don't know is Q. So the first question becomes is what exactly is Q? Well, remember that what we're doing here, and maybe I'll scroll up to the picture to really emphasize this, is we're rotating our basis. We're not rotating our specimen. We're rotating our basis. So therefore, this is a basis rotation. I'm going to put that down here, a basis rotation. And the reason why I'm emphasizing that is you guys have gotten used to rotating shapes. So what you guys would do is you'd take your rotation matrix, say for a counterclockwise rotation, and then you guys would flip it over to a clockwise rotation. That's not needed here because we're rotating the basis itself. So we know that Q is going to be equal to, and let's put, I'm trying to make this nice. It's my first time writing without the lines, but you know, it's time to take those training wheels off and kind of grow up a little bit. So if we're rotating the basis, the first thing we got to figure out is which way are we rotating it? Well, if we look up above, and we can easily tell by the arrows, this is going to be a counterclockwise rotation of the basis. So I'm going to come down here, basis rotation of counterclockwise. So I'll put CCW just for reference. Well, I remember that is cosine of theta. Well, we already know theta is 45, so I'm just going to save me the effort. And I don't even know what I was trying to draw there. Down below, we have negative sine of 45. So again, this is just your typical counterclockwise rotation. You guys have seen this a million times. Over here, we have sine of 45. And then right here, we have cosine of 45. So a lot of you guys will say, well, what are the other entries? Well, they're simply just going to be 0, 0, 0, 0, and 1. Not too bad, nothing too crazy, nothing too special. This is going to be our change of basis. Now I'll switch colors once again, and I think I'll keep switching colors to kind of show you guys what the steps are. So right now we're interested in sigma prime because now that we know what our Q is, so sigma prime is equal to Q, well, we know that, that's right above, multiplied by sigma. If we look up here, there's our sigma, so we also know sigma, and then multiplied by Q transpose, so Q transpose, we can figure out what our stress is in the coordinate system that matches those material properties. And luckily for us, it's something that's actually not too bad. So it's 50, negative 50, and of course it's symmetric. It'll always be symmetric. So if you guys multiply two matrices and it turns out it's not symmetric, something's a little bit off. So I recommend you guys check. So 50 and then 0, 0, 0, 0, and 0. So as you guys can see, I'm struggling a little bit without the lines, but I don't know. I think it looks a little bit better without the lines. If you guys prefer the lines, please let me know and we can go back to how the lines were. Again, I feel like this is just how you guys want it. All right, so now that we have the stress in the coordinate system and we have the properties, we can go to the next fun step, which I know you guys love so much. And let's say we do this in orange. Let's see how it looks. All right, yeah, actually that looks pretty good. So we know that the strain vector is going to be equal to the elasticity tensor minus our stress vector. And of course, from above, we can easily figure out our stress vector. The elasticity tensor, this is going to be the only thing that's throwing a wrench into our plans. So the elasticity tensor depends on the material properties. But we already know that we're given all those material properties. Here's where students will start diverging from the right answer. They will use the isotropic tensor with one single E and one single V. If you guys do that, you guys are obviously going to get this wrong. We need the orthotropic elasticity tensor, which I'm going to draw below right now. All right, and here it is, the orthotropic elasticity tensor. And wow, it was terrible to try and draw out. So I hope that you guys appreciate it. I really don't like drawing it out, but of course you guys are absolutely worth it. So don't let anyone tell you guys are not worth it. You guys are absolutely worth it. So if we look at this tensor, we need 9 parameters to define this bad boy. And of course we're given all 9 parameters, so that's not going to be too bad. Now, quick notes of it is symmetric, even though it doesn't look like it's symmetric. So let's take a look at two components that are supposedly symmetric. On the one side, we have negative V12 divided by E11, and on the other side, we got negative V21 divided by E22. So what happens is we can actually know that it's symmetric. So all I'm going to have to do in this type of problem, as you guys will see, we're only given V12. So what's going to happen is we're going to figure out what this value is, and we're say, oh yeah, that's the same as this value over here. And we're going to have to do that with the remaining values, so of course we're going to have to do that with this one. Well, that one's going to be equal to this one. What about this one? Well, this one's equal to this one. So this is why it appears as though we don't have enough material, but we actually do, because we're not given V21 or V31 or V32. However, since we know V12, V13, and V33, we can solve for those 3 components, and then since we know it's symmetric, we just simply apply it to the other side. All right, so now let's look at our stress vector. Of course, I just put it as sigma 11, sigma 22, etc., etc. However, we actually already know the values, so I'm going to erase them really quick, and we're going to fill in our actual values. So if I scroll up to the top here, we see that sigma 11 and sigma 22 are both equal to 50. So I'm going to come down here and say, all right, well, I know that this bad boy is 50. This one's 50 as well. And if we look, there is no sigma 33, so this is going to be a big fat 0. Now, when we look at the shear, we do have shear in sigma 12, and that is negative 50. So right here we have a negative 50, but of course there's no shear in the other 2 directions, so those are just going to be big fat zeros. All right, so looking at this now, I hope you guys realize, well, we can solve for the strain. The only thing that we need, of course, is all the components of the elasticity tensor C. And right now, I wrote them in terms of 1, 2, and 3. So what we're going to have to do is try and figure out our axis relationships. So if we come back up here, we're going to scroll up to the top really nicely. We know that 1, well, that, and I'll switch colors to really make this more clear. When we went to E1, that transformed to EL. So if we're ever given, let's say, Young's modulus 1, 1, well, that's the same as E of L. We look at the 2, Well, the 2 came down and became our radial one. So anytime that we have a 2, we can substitute that with r. And of course, we can finally do that with 3. We come down here, and the 3 turns into a t. So let's go down here and just pick an example so you guys can see exactly what I mean. Let's go to the highlighter, and let's take this one right here where we have, because that's one of the symmetric ones. I'll explain why I did that in a second. So let's take this one right here. So we got negative v12 divided by e11. So I'm just going to scroll up here. I'm going to write that down kind of in a little, let's go blue. We got negative, and not highlighter, of course. I don't want that in highlighter. I want it as a pencil. We had negative v12 divided by e11. Well, of course, we can use our notation. So we have negative v. We know that the 1 is actually L. What is the 2? Well, the 2 is R divided by e11. So this would be E L. And I don't know if they did it as L in the table or just L. Yeah, they just simply did it as L. So we can make that quick distinction, that quick swap really quick. However, it's nice because, again, if you guys threw this in Mathematica, then all you guys are going to have to do is say that V12 is equal to, and you guys can actually input the actual number. Now, the reason why I threw off the other one is because, again, we are not given, if we look at that table, we're not given V21. So we're going to have to use the symmetry in saying that, and I'll kind of erase these two. This as a whole is equal to this as a whole. So I can come up here and say, well, that VLR, well, that's actually equal to negative V21 divided by E22. So this is why we're going to have to use that symmetry, because again, there's 6 different Poisson's ratios, but we're only given 3. That's how we use that symmetry to solve for the rest of the question. All right, so now that we know everything in that C matrix, we know our stress vector, we can easily find our strain vector. So again, I'm going to do a quick cut and have that strain vector presented right now. All right, so the strains were quite long, but in essence, this is what we got. We have non-zero components for E11, E22, and E33. And then for the first time ever, we have a non-zero shear strain. So if we look at epsilon 1, 2, I have that value as negative 0.0488. And this is going to be really special because, again, this is the first time that we've seen that non-zero shearing strain. And this actually has some special implications. And this will be something that I guarantee half of the students will forget in their midterm, and it makes for an easy question to try and trick the students. So right now we have a strain vector. Of course, we don't want a strain vector, we want a strain tensor. So I'm going to come down here and say, okay, well, I have my vector. I know how to make it into a tensor again. So I know that my tensor, and of course, I'm not talking about stress. I don't know why I decided to do that. So I'm going to try and make this as nice as possible. Ooh. My perception of a straight line is so off. I don't know if you guys know this, but I actually write sideways. I have my iPad actually rotated 90 degrees right now, so it's very hard for me to tell where a straight line is, obviously. So if I'm converting the vector back into the tensor, well, first component I want, that's going to be epsilon 1, 1, and I shouldn't be using blue highlighter because I got a blue background. Let's switch this. Ooh, let's try the pink. Epsilon 1, 1, well, of course, that's just going to be this component right here. So I have 0.00132. That's my first component. Well, how about the next one? Of course, I have epsilon 2, 2, which is going to be this over here. So I can come down and say, all right, well, the next one is going to be 0.03194. Not too bad. I can say, all right, well, how about the next one? Well, that's going to be epsilon 3, 3, which is our first negative component. So what I get is, I'm just going to scroll down a little bit, guys, because my hand has fallen off the iPad. 0.01637. And I made this matrix C a lot bigger than usual. And of course, my shear in the directions 1, 3, and 2, 3, I have 0 shear strain. So these are going to be 0. So then the only thing that's left, of course, and I'm going to finish out the brackets first because the next thing I want to talk about, I'll probably ramble on about because it's so important. It's one of those questions that makes students lose a lot of marks on their midterms, and I really don't like it when you guys fall for little tricks. I think that tricks are the most evil thing a professor can do. So let's try and prevent that right here by talking about the shear strain. So I'm going to put this in a different color so you guys know that I mean business. So our shear strain right here, Well, we can say it's negative 0.0488. Now, what a lot of students will do is put negative 0.0488. And that'll get you the wrong answer guaranteed. The real bitch to this, and I don't want to swear too much anymore moving forward. I'm trying to get a little bit better. But this one's honestly a bitch, so I gotta be honest with you guys, because that's very important. This 2 right here will screw up so many students. So many students. So keep in mind that epsilon 1, 2 isn't equal to negative 0.0488. 2 times epsilon 1, 2 is equal to negative 0.0488. So if I want the value of epsilon 1, 2 by itself, what I actually have to do is divide by 2. So of course, negative 0.0488 divided by 2, the actual value of epsilon 1, 2 will be negative 0.0244. And that actually looks kind of nice with the blue, kind of a Hotline Miami vibe going on. All right, but yeah, on a serious note, this is very important. Please don't forget the implications of having that 2. I wasn't able to talk to you guys about this before because, of course, we didn't have any shearing strains, but now that we do, make sure that you guys divide them by 2. If you guys forget to divide them by 2, you guys will get the question wrong. All right, so now that we have our strain, the question seems done, right? I can throw this into E-class and get my marks and have a good time and go party for the weekend. Well, no, it's still not that simple. This question's really, really tricky. So what happens is our stresses that we inputted into here, these were in the basis set B prime. So I'll come down here and let's switch the highlight color. We solve for the stresses in B prime. But the question, being the question it says it wants it in the original coordinate system B. So it says you found the stresses in B prime. Great. I don't give a shit. I want them in B. So what are we going to have to do is, well, we're going to have to take our stresses that we have and convert them back. So notice that we're in B prime right now. So when I come down over here to the strain, this isn't technically the strain. This is the strain in prime. And we had to figure out, all right, well, how exactly do we get it back? Well, there's actually 2 options that we can do. There's the simple way and there's the little bit more complicated, but still a little bit simple way. So one of the first ways, which is what I did at the beginning, but Dr. Sammer said, what are you doing? There's a much easier way, and I completely agree with him. As I said, all right, well, to go from B to B prime, I rotated counterclockwise. All right, so if I want to go from B prime to B, well, I'm going to rotate, except this time I'm going to go clockwise. Seems easy enough, not too bad. However, simpler formulas can be developed if we look at the formula right here. So of course, we have sigma prime is equal to Q times sigma times Q transpose. And what I can do down here is apply the exact same thing. So I can say that E prime is equal to Q. And this Q right here, this is still the counterclockwise. This is the same Q I used before, times E times Q transpose. And I can say, all right, well, before, and I'll switch colors here, before I had this one, and then I converted to this one. Well, now I have this one, and I want to convert to this one. So how do I do that? Well, I just do some nice matrix rearranging, and I can say, all right, well, my strain E now, and this is in B, this is not B prime, so I'm going to put in B, is equal to Q transpose times the strain times Q, and this one's E prime. So this right here, this is the one now that's in B prime. So if you guys realize, all we're going to do is transpose that first Q matrix instead of transposing the second one. So now if I look here, I say, all right, well, my highlighters always align with each other. My first thing is, all right, well, what is Q? Well, Q is defined right at the beginning. Again, I'm not switching the Q matrix at all. This is my nice Q right here, already defined, already good to go. The second part, what is my strain prime? Well, that is going to be this value right here. So right now I can say, all right, well, I have everything I need in my equation. I can go ahead and solve. And what I get once I throw all this in is that my strain, and this will be the strain in E. So this is actually my final answer, is going to be as follows. 0.00132, and I get negative 0.0. Oh, wait, hold on one second, guys. This is the strain E prime. Sorry. It's the end of the example. Of course, you guys can expect that I would blow up all my momentum and mess up badly. So the first component is actually 0.0410. The first shear component below it is going to be negative 0.0153. The shear strain 1,3 is equal to 0, so that's nice and easy. Moving on to the second column, of course, it's going to be symmetric, so we already know that this is going to be the 0.0153. The the strain in the 2,2 direction is negative 0.00, so 2 zeros this time, 78. The shear in the 2,3 direction is equal to 0. Moving on to the third column, of course, this is symmetric, so we know that this one's going to be 0, and this one's going to be 0. And finally, my last component is negative 0.0164. And this, ladies and gentlemen, is the final answer. So it took us a while to get here, but this is the final answer in the end. If you guys throw this into your class, you guys will be just fine. So since this was a long question, I just want to do a quick little recap to make sure you guys understand the process of this question. So we were given a question, an orthotropic tensor, sucks ass, but we were able to solve it, and this is how. We realized that the loading and the material properties were in different basis coordinate systems. So what did we do? We converted the loading into the material properties coordinate system. How do we do that? We did a nice transformation matrix Q, and we applied our formula that we already know, where sigma prime is equal to Q times sigma times Q transpose. Once we had the stresses in the material properties coordinates, well, then we were able to use our elasticity tensor for an orthotropic material to take those stresses that are in those material properties coordinates and find the strains in the material properties coordinates. So keep in mind that this whole elasticity tensor, it was all done in the material properties coordinates, aka the longitudinal, the radial, and the transverse direction. Sorry, I'm getting a little lost here. With the strain vector here, I was able to transform it into a strain tensor. Again, the big thing that I want you guys all to remember, please, and do this for me, I want to see no one fall for this trap on the midterm, is we remember that when we're talking about shear strains, there's that nasty little 2 out above. So of course, when we're converting from the vector down to the tensor, we had to divide by 2 whenever we're considering a shear strain. All right, that's great. We have our strain tensor, but the problem is, again, this is still in the material properties coordinate system. So what we want to do is we want to revert back into our original E1, E2, and E3. Well, what we did is we took our same transformation matrix as before, and we just rearranged the formula. How do we do that? Well, instead of going Q, E times Q transpose, we started off with a Q transpose and then finished off with an E times Q. And in the end, we were able to get our final answer. So that's it. That's all. That was question number 5. I know, really beefy question, but I really hope I helped you guys. I know I tried to put as much detail in the video as possible. Sometimes they're probably a little bit longer than I would have liked, but of course, it makes me feel a little bit better that if you guys are having the troubles, I try and highlight every part of this question for you guys. So again, a new video format. Of course, there's going to be some hiccups, some bumps along the way. Please tell me what you like, what you don't like, and if you guys have any suggestions for the future. Thank you guys so much for listening. I really appreciate it. Again, I hope these videos are helping you. These are for you guys. These are not for me. So if there's, again, anything else that I can do to help you guys, please let me know. All right, guys. Thanks again so much for listening. I will see you guys in quiz number 23.